Right now, somewhere in the middle of the Dubai desert, the tallest building on Earth is doing something that most people have never stopped to think about. It is moving, slowly, silently, downward. And if you have ever wondered whether a building this massive, sitting on nothing but sand, can actually hold itself up forever, the answer may genuinely surprise you. We are talking about the Burj Khalifa, 828 meters tall, 163 floors, 500,000 tons of steel and concrete pushing straight down into desert ground. And the question that engineers, physicists, and now millions of people online are asking is simple. Is this thing sinking? And if it is, what happens when it stops? Stay with me for the next few minutes, because what you are about to hear is not a story about a building. It is a story about one of the most ambitious engineering gambles in modern history. A $1.5 billion calculation built on sand, salt water, and physics. And so far, the engineering has performed remarkably well. But the story of how they got there is unlike anything you have heard before. Before we go any further, quick favor. If you are the kind of person who loves stories about massive engineering, insane science, and the moments when humans push too far, hit that subscribe button right now and tap the bell. We drop content like this every single week here on Strategic Dynamics Edge, and trust me, you do not want to miss what is coming next. Now, back to Dubai, back to the sand. Here is something most people do not realize. The ground beneath Dubai is not normal ground. It is not the kind of earth you find under New York or London or Tokyo, where builders can drill down and eventually hit solid bedrock. No. In Dubai, you drill down 10 meters, sand. You drill down 100 meters, weak, crumbling rock. You go all the way to 140 meters deep, the height of a 45-story building. And you find absolutely nothing solid, just layers of loose desert sand sitting on top of compressed ancient seashells. Shells from oceans that dried up millions of years ago. This is the ground that the Burj Khalifa is built on. Now think about that for a second. 500,000 tons of weight, pushing down, every single day, on sand and crushed shells. If you pressed a single finger onto wet sand at the beach, it sinks immediately. So what happens when you place something 500,000 times heavier onto desert sand? Physics suggests the ground should compress significantly, and that raises a very real engineering challenge. This is not a hypothetical. We have seen it happen before. And the story of what went wrong in San Francisco is exactly why what happened in Dubai is so extraordinary. In 2009, a luxury skyscraper called the Millennium Tower opened in San Francisco. 58 floors, premium apartments, multi-million-dollar views. People were paying fortunes to live there. And within just 7 years of opening, something quietly terrifying began happening. The building started sinking, not a little, 18 inches into the ground. That is almost half a meter, straight down. But here is the thing that makes this truly dangerous. It did not sink evenly. The northwest corner started dropping faster than the rest, which means the entire building began to tilt. Floors became uneven. You could literally feel the slope beneath your feet walking through the hallways. Walls cracked. Residents started panicking. And here is what makes it worse. It is still sinking today, right now. As you are watching this video, the Millennium Tower is still moving. The cause was straightforward. Engineers built the foundation on soft clay and assumed that friction alone would keep it in place. The clay kept compressing under the load, year after year, pulling the building deeper, and uneven compression caused the tilt. The lesson from San Francisco was brutal and expensive. You cannot take risks with the ground beneath a skyscraper. Because once a building starts moving the wrong way, there is almost nothing you can do to stop it. Now take that lesson and multiply the stakes by 100, because that is exactly the situation the engineers faced in Dubai. Except instead of soft clay, they had something far less forgiving: loose sand, desert temperatures, and corrosive salty groundwater eating through everything underground. This is where one man stepped in and made the decision that changed everything. Everything you are about to hear is based on publicly available engineering data, structural reports, and documented construction history of the Burj Khalifa. This video is for educational purposes and presents engineering facts in a narrative format. The dramatic scenarios described are based on structural physics, not any reported incidents or safety failures. The Burj Khalifa is currently a fully operational and monitored structure. His name is Bill Baker, Chief Structural Engineer. The man handled one of the most ambitious construction projects ever attempted. And his first job was simple: find bedrock. Baker's team drilled and drilled and drilled and found nothing solid, no bedrock, just layers of sand and ancient compressed shells going down further than any foundation could reach. For most engineering teams, that would have been the end. You pack up, you go home, you tell the client it cannot be done. Baker did not go home. He spent the next phase of planning rethinking a fundamental assumption. What if you did not need bedrock? What if there was another force, a different kind of grip, that could hold 500,000 tons in place without any rock at all? The answer came from something you have probably done yourself without ever thinking about it. Take a pencil, push it into sand. At first it goes in easily, but the deeper you push, the harder it gets. Not because you hit anything solid, but because the sand on every side of that pencil is gripping it. Friction. The deeper the pencil goes, the more surface area is touching the sand, and the stronger that grip becomes. At a certain depth, that pencil is not going anywhere, even without hitting rock. Baker scaled that principle up, way up. Instead of one massive anchor, he designed 192 individual concrete piles, each one 1.5 meters wide, each one driven 50 meters deep into the ground. Together, their combined surface area in contact with the earth generates a gripping force so powerful that it holds 500,000 tons without moving. Each individual pile carries 3,000 tons of load. Together, they have a total capacity of 576,000 tons, with a safety buffer built in on top of that. Drilling those piles nearly broke the project before it began. The moment engineers removed soil from the shaft, salty groundwater rushed in and collapsed the hole from the sides. They had to pump heavy drilling fluid down each shaft just to keep the walls open long enough to lower steel reinforcement bars and pour liquid concrete. It took 2 full years just to complete the foundation. Before a single floor was built above ground, 2 years had already passed. But weight was only the first problem, because beneath the surface, something invisible was already working to destroy what they had built. Dubai sits right next to the Persian Gulf. Salty groundwater is literally everywhere underground, and salt water does one thing to steel with brutal consistency: it corrodes it. Slowly, invisibly, from the inside out. Without protection, every one of those 192 steel-reinforced concrete piles would begin rusting within decades. The steel would weaken, the friction would start to fail, and a building carrying 500,000 tons would begin to move. Engineers installed something called a cathodic protection system. In simple terms, they run a constant low-level electrical current through the entire foundation, 24 hours a day, 7 days a week, every single day since the building opened. This current pushes electrons onto the steel bars inside each pile, chemically preventing rust from ever forming. A sacrificial titanium mesh surrounding the foundation absorbs the corrosion instead, slowly degrading so the steel never has to. The system is completely invisible. You will never see it, but if it ever shuts off, the clock starts ticking on the foundation's lifespan. Friction holds the weight. Electricity protects the steel. 2 invisible systems, running constantly underground, are the only reason a 500,000-ton tower is not slowly disappearing into the desert floor. And even then, one final threat remained. And this one was coming from every direction at once. Here is something that most people get wrong about skyscrapers. The thing that actually destroys tall buildings is not usually the weight. It is the wind, but not wind in the way you might think. When wind hits the face of a tall building, it does not just push straight through. It wraps around the edges and creates spinning columns of air called vortices. These vortices alternate sides, left, right, and each time they switch, they give the building a small sideways push. If those pushes happen to match the building's natural vibration frequency, the sway starts compounding. Every pulse adds to the last one. The building swings further and further until the structure fails. This is called resonance, and it has brought down bridges. It has shattered windows in skyscrapers. Left unchecked, it can bring down an entire tower. Bill Baker solved this problem with the shape of the building itself. The Burj Khalifa is Y-shaped, 3 wings extending out from a central core, and that Y shape changes 27 times as the building rises. Every few floors, the width shifts, the angles change, the profile of the building transforms slightly. Why? Because every shape creates wind vortices at a different frequency. If the shape keeps changing, the wind can never find a rhythm. It can never push the building in sync with itself. The vortices from each section of the building cancel each other out before they can build into anything dangerous. On top of that, the upper 25% of the tower is built primarily from steel rather than concrete. This was deliberate. Steel bends, concrete cracks. When the wind is extreme, you want the very top of a building to flex, not fracture. As a result, the tip of the Burj Khalifa can sway up to 6 feet in strong winds. And that is not a defect. That is engineering working exactly as intended. The tower is designed to survive winds of 240 kilometers per hour, stronger than a Category 4 hurricane, and do it without a single crack. So now we come to the question you came here for. The real answer. Is the Burj Khalifa actually sinking? Yes and no. And the difference between those two answers is everything. Every building on Earth settles. When you place a massive structure on any kind of soil, the weight compresses the ground beneath it over time. This is expected. This is calculated. Before construction began, engineers predicted the Burj Khalifa would settle approximately 100 millimeters, about 4 inches, as the soil compressed under the load. That was the plan. The reality? It settled only 50 millimeters, less than the length of your thumb, half of what was predicted. And here is the most important part. It settled perfectly evenly, no tilt, no lean, no uneven drop on any side. Compare that to the Millennium Tower in San Francisco, sinking 18 uneven inches and still tilting today. The Burj Khalifa, sitting on desert sand, performed better than a luxury skyscraper built in one of the most geologically stable cities in America. This was not luck. Baker's team placed the 192 piles strategically at the outer edges of the foundation to distribute the load as evenly as physics allows, and sensors embedded throughout the foundation track movement down to a single millimeter, 24 hours a day. If anything shifts even slightly, the system flags it immediately. At this point, those concrete piles are not just held by friction, they are embedded in compacted sedimentary material so dense that for them to move, they would have to physically shear through rock. That is not going to happen. Back in 2004, when construction started, skeptics said it would sink. In 2009, when it opened, critics said the foundation would fail within years. Every single time, the building proved them wrong. And it continues to do so today. Here is what this building actually cost in human effort. Beyond the money. 6 years of continuous construction, 12,000 workers on site every single day, 22 million total work hours. Concrete that had to be mixed with ice and poured exclusively at night because Dubai's 50-degree temperatures would cause it to cure too fast and become brittle during the day. The shape of the building was inspired by a desert flower, the Dubai spider lily, and those petal-like forms at the base are not decorative. They are structural buttresses that channel the entire weight of the building straight down into the earth. And at the very top, a lightning rod that protects not just the building, but the entire city block below it. The Burj Khalifa is not sinking. It is the proof that when human beings are determined enough, when the math is right, when the engineering is honest, and when the team refuses to walk away from the impossible, they can build the sky itself on a foundation of sand. But here is the thing. The Burj Khalifa's time at the top may be running out. While Dubai conquered the desert, engineers in Saudi Arabia have resumed construction on the Jeddah Tower. It has already passed 100 floors and is targeting a height that would make the Burj Khalifa look like a warm-up act. Will it succeed? Can any structure go higher than what was built in Dubai? And what engineering problems does building even taller create that no one has solved yet? That is the next video. And trust me, it is even more unbelievable than this one. If this video changed the way you look at the skyline, drop a comment below. Would you stand on the 163rd floor knowing everything you know now? Let us know. Share this with someone who loves engineering or would never believe a building this tall is sitting on sand. And if you have not subscribed yet, now is the time. Hit subscribe and the bell so you never miss a video from Strategic Dynamics Edge. The Jeddah Tower video is right on your screen. Click it now. I will see you there.